Okay, so this is there are two degenerate cases. This is a degenerate case, unbounded solution. So x can go up to infinity, or some xi can go up to infinity. So the solution could be unbounded, or there could be no solutions at all. All the constraints must be satisfied in the first quadrant, and sometimes that's not possible. So you might not have any solution. Okay, so we can, given any linear programming, we can also try to manipulate the constraints to suit us better. So suppose we have an equality constraint. A transpose X equals B. Okay, now let's take up a case where we have just a single inequality constraint. Okay, so A transpose X equals B, or summation J, AJ XJ equals B. That's our constraint. Yeah?
So what is the advantage to observe the corners of the feasible region?
Oh, the solution, optimal solution it's not an advantage. The optimal solution will always lie in one of the corners.
Doesn't it depend upon on f of x function?
See, I told you that these contours of f of x, C transpose x, are not parallel to any of these boundaries.
Okay.
That's because that the C is linearly independent of the rows of A. Okay, thank you. Thank you. Okay, so where were we? So this is a single equality constraint. So how to handle this? One approach is variable elimination. So we pick any variable xj for which aj is not equal to 0. No, it's not. Now it's on. Now it's off. Okay. Yeah. So, okay. So, as I was able, exercise, and then And then okay, so hello? Does it? Yeah, we're good now. Start. See, okay. So the constraint reformulation is, suppose we are given an equality constraint, summation j, x, aj xj equals b, which is the same thing as this. Then there are two approaches to address this issue. Eliminate a equality constraint. One way is variable elimination. So we pick any variable xj for which aj is not equal to 0. And then we express this aj using this equation here as a linear combination of the other scalar variables xi. And then in the objective function and the constraints, in all the objective, constraints and the objective function, we eliminate xj using this expression. So that's one way to handle an equality constraint. Another way to handle an equality constraint is just replace the equality constraint with a pair of inequality constraints. So if you have an A transpose X equals B, it can be replaced with A transpose X is less than equal to B and A transpose X is greater than equal to B. Now, there is another way to handle linear programming, that is where you only have equality constraints. That's called the standard form as opposed to the canonical form. Okay, so here, if you have an inequality constraint, you must replace with an equality constraint. Here's how. So we are given A transpose X is less than equal to B. We create a dummy variable, it's called a slack variable. So what we do is we introduce another variable xs, the slack variable. And this A transpose X is less than equal to B can be replaced with these two. A transpose X plus xs equals B, where xs is greater than equal to 0. And this xs is called a slack variable. Suppose you have an unrestricted variable. So far, we are considering each xi must be greater than equal to 0. Suppose you have some variable x that can lie anywhere in negative infinity and plus infinity. So suppose you have an unrestricted variable that can also become negative. So we have an x like this. So what we can do is replace this x with two variables, xa and xb, in the objective function and all the constraints. We can do this. So x equals xa minus xb. Okay, and we'll let xa and xb be greater than equal to 0. So when xb is greater than xa, then that means that x is negative. This way, we are allowing the entire range of values of x. Now, here's a application, max flow, an application of linear programming. So we have a digraph with source and destination nodes and weights. So this is a digraph. okay, or a directed graph, it's weighted. So you have all these weights, and directed graph means, so you have 1, 2, 3 until 6. These are the nodes or the vertices, and these are the edges. The edges are directed, okay? 1 to 2, you have an edge. You don't have an edge from 2 to 1. But when you have bidirectional arrows like this, you can think of this as a pair of edges. One edge from 2 to 4 and another edge from 4 to 2. Similarly, for this bidirectional edge, the rest are along one direction. Okay, and then you have a source and a destination. Okay, so think of it as a source of water, maybe. So this is a source of water, and you want to supply water to the destination. And these are the conduits or the pipes along which water can flow. Okay, so, and these are the capacities, maximum capacity. So along this pipe, you can have a maximum flow of 1.2. Along this pipe, you can have a maximum flow of 1.0. Now, this is a pair of pipes, right? One from 4 to 2 and 2 to 4. So you can have, so these are the capacities of those pipes. These are the capacities. Both ways, the capacity is 3 in this case. Okay, and likewise for the other edges. So edge weights are the maximum capacities. So we have to maximize the total flow. Okay, so in other words, what's the total outflow from the source? Whatever flows out from 1 to 2 and from 1 to 4, sum them up together, that's the total outflow. What's the total inflow into the destination? From 3 to 6 and from 5 to 6, right? Add them up, you get the total inflow into the destination. Both of them will be the same if we design our constraints appropriately. So let's say we want to maximize the outflow from the source. Okay, so what we do is for each edge, let's say this edge is 1 to 2, we create a variable x12. We'll have two variables, x24 and x42, because this is a bidirectional edge. Okay, so x12 is the flow from 1 to 2. And in general, xij is the flow from node I to node j. Okay, so here's the LP formulation. Maximize the total outflow, x12 plus x14. And what are the constraints? So these are the constraints. These are the capacity constraints. x12 cannot exceed 1.2. That's the capacity of this. Note, of course, all these x's must be greater than or equal to 0, right? Okay, and so I write down for each edge we have a capacity constraint. So these are the set of capacity constraints. We also have another set of constraints. These are called the flow constraints. See what happens? There is no storage available at each of these intermediate nodes. One has infinite storage from which it's flowing, and this has infinite, it's an infinite sink. Okay, but there's no storage in any of these. So the outflow from every of these nodes, intermediate nodes, 2, 3, 4, 5, must equal to its inflow, correct? In other words, what's the inflow into node 2? x12 plus x42. What's the outflow? x23. Okay, x23, and well, you can have a separate outflow, x24. So that gives rise to this constraint. The total inflow into node 2 must equal the total outflow. And so for each of these intermediate nodes, you have one of these flow constraints. So you have all the flow constraints. How many capacity constraints altogether? Equal to the number of edges. where bidirectional edges count as two separate edges. So you see 7 arrows here, but here you have a total of how many? 10 constraints. And how many of these flow constraints? If n is the total number of nodes, remove 2, the source and the destination, you have n minus 2 intermediate nodes, and so you would have that many flow constraints. Additionally, all these x's must be greater than or equal to 0. How many variables would you have? Well, in general, up to n square, where n is the number of nodes, but it will be, number of variables will be equal to the number of edges, with the bidirectional edges counting as 2, which would be equal to the number of capacity constraints. Okay, so this is a simple application of linear programming. Another application, fractional programming. So our objective is to minimize this. C and P are two vectors, constant vectors, and X is our design variable, and D and Q are two scalar constants. And this is what we have to minimize. Okay. And of course, it goes without saying that, well, we have one AX, this is one constraint that we have, AX is greater than or equal to B, and it goes without saying that the denominator cannot be equal to 0, right? Well, to begin with, we want to minimize. If the denominator becomes 0, then this would be plus infinity, or actually it could be minus infinity too. So, well, in that case, the linear programming formulation that will follow, I'll show you, will be unbounded. Okay. Okay, so these are the constraints that we have. P transpose X plus Q is greater than 0, not greater than or equal to 0 because of this. It's in the denominator, and X is greater than or equal to 0. So here's what we do. We will replace X with other variables. Okay, so let Z be equal to 1 over the denominator, which is 1 over this, P transpose X plus Q. Z can never be 0. Okay, Z will always be positive. It will always be strictly positive. Okay, and Y equals X divided by the denominator, just this X divided by the denominator. Then what will happen to our objective function? Let's look at this D over denominator first. It will be dz, correct? With this, what will C transpose X divided by the denominator be? C transpose Y, correct? C transpose X divided by denominator, just take C transpose. So if this is X divided by denominator, then C transpose X divided by denominator will be C transpose of this, which is C transpose Y. So we have a change of variables here. And so now this looks like a linear objective, right? C transpose Y plus dz. The second term is dz corresponding to the second term here divided by the denominator, and C transpose X divided by denominator gives you this. Okay, and so what are the constraints? Subject to AX greater than or equal to B is the same thing as AY greater than or equal to BZ. I pre-multiplied both sides with Z, which is greater than 0, so this greater than or equal to will not change. It won't be a less than or equal to, because Z is greater than or equal to 0, greater than 0, and so we have this constraint. AX becomes AY now, AZX becomes AY, and BZ is this. So this is a linear constraint. And we must have z is greater than or equal to 0 and y is greater than or equal to 0. Because why is y greater than or equal to 0? That's because the denominator is greater than or equal to 0 and x is also greater than or equal to 0, element-wise. Okay, so which implies that y must be greater than or equal to 0. Of course, if z equals 0 here is the solution, then we have to discard that solution. Okay? So this is fractional programming that we have reformulated as a linear programming problem. Yes? Oh, it's simple. See, this is what we have to minimize. Okay, now consider the first term, C transpose X divided by denominator. X divided by denominator is Y. So what's C transpose X divided by denominator? It will be C transpose Y, right? Yeah, so that's how we, the question was, how do you arrive at this objective? And I'm sure you can see how it is d divided by denominator becomes dz. Okay, so this is fractional programming. Another application, L1 norm minimization. So we have to minimize with respect to x. A is a matrix, x is a vector, minus b is a vector. The L1 norm of ax minus b. Now the ith element, so this is a vector, right? Ax minus b is a vector. The ith element of this vector would be of this form, summation aij xj minus bi. Okay, and so we have to minimize with respect to x this. This is by definition the L1 norm, right? How do you compute the L1 norm of a vector? Take the absolute values of all the elements and then add them up together, right? Summation of all the absolute values of all the elements. This is the notation for the ith element of a vector. And here I've replaced this, these kind of brackets with the absolute operator. Okay. So the absolute value of this is one of the terms here. So this is what we have to do. What I do is I create another set of variables. For each of these elements, I'll create a variable yi. So I'll let yi be equal to the absolute value of ax minus b, the ith element of that. Which implies that since it's an absolute value, it will always be greater than or equal to 0. Okay? And now, in terms of y's, what does the objective function be? Summation of the yi's is what I have to minimize, correct? So, this is what I have to minimize. You'll see x and y will have to consider both sets of variables. Okay, so this is what we want to minimize. Now, simple question would be, why doesn't x appear in the objective function? Well, you can think of it this way. Objective function is 1 transpose y plus 0 transpose x. It involves all the variables. In general, the objective function need not involve all the variables. The constraints, likewise, need not involve all the design variables. Okay, so now this is what we want to minimize. For each yi, this is the x, yi axis, and the center point is the origin. Okay, so this is plus yi and this is negative yi. And what we want to do is, we want to minimize each of these yi's. Since we're trying to minimize the summation of the yi's, individually we're trying to minimize each of these yi's. Correct? So when we do the minimization, we're trying to move the plus yi's in this direction and the negative yi's in this direction, the opposite direction. Okay, so we're pushing them both towards the origin. And since yi's are all greater than or equal to 0, we have to add these constraints, y greater than or equal to 0. And then think of these as the lower bound and upper bound now. Okay, so x and y are independent now, so we have two sets of variables. Okay, so since y's and x's are independent, so we have yi, negative and positive yi's are the lower bounds and lower and upper bounds of ax minus b I, the ith element A of the vector ax minus b. Are we clear with this? Okay. There's an example which might make things clearer. Okay, and then, so these are our constraints. And so each element I of ax minus b will have to lie within this region. And simultaneously, we minimize x and y. So these are our constraints. So the resulting LP problem is this. Okay, this is our LP problem. Minimized with respect to x and y, 1 transpose y subject to these are our constraints. And it goes without saying that if x star, y star denote the solution, optimum, then if the ith component of ax star minus b is less than 0, then negative yi star equals this. So it hit the lower bound. Otherwise, if ax star minus b is positive, the ith element is positive, then absolute value here is the same as this, which is so plus yi star equals ax star minus b ith component. I know this is a little confusing, so let's take up a simple example. Okay, so we are given a and b and x here, and this is ax minus b. Okay, this x1, x2 are the two design variables. And this is what we want to minimize with respect to x. This is ax minus b. Its L1 norm is, we just take the absolute values of the different elements and add them up together. Okay? Now we let y1 be equal to this first term here in the objective, and y2 become the second term. And so this is, according to the previous slide, so this is what we want to minimize, y1 plus y2, where y1 and y2 must be greater than or equal to 0 because they are absolute values of some things. And our constraints are this 2x1 plus 3x2 minus 3 must strictly lie between negative yi and yi. I misspoke. No, strictly. It must lie within negative yi and plus yi. Negative y1 and plus y1. Likewise, this second element of ax minus b must lie within negative y2 and plus y2. Okay, so we'll understand how this works. Now, note that we have two inequalities here. Okay, so it's actually a set of two inequality constraints. Okay, are we good so far? Okay, so what I've done is I've split these inequality constraints into these bounds, negative the lower and upper bounds into a pair of inequality constraints. And the same thing for this guy. So I have 4 inequality constraints. Okay. Now, what's going on here? Let's pretend that x1 and x2 are fixed. Okay, so x1 and x2 are fixed at some value. And so, this 2x1 plus 3x2 minus 3 evaluates to some value here. And likewise, the second element of ax minus b, which is this, evaluates to some other value. So these green dots here correspond to the actual values when x1 and x2 are fixed. Okay. And so we are trying to minimize with respect to y1 and y2 alone. What should we do? So each variable yi, so y1, for instance, when we're trying to minimize, it means that these bounds, which are negative y1 and plus y1, are moving inwards, right? And likewise, due to this minimization, y2 is also separately getting minimized, and so these bounds, negative y2 and plus y2, are also moving inwards. Okay, now when will they stop? So as we start from some values of y1 and y2, and then we gradually decrease them. Okay, so when will they stop? We have these constraints, right? So this and this, so these two are this green point here, and these two correspond to this green point here, right? And to preserve these constraints, right? So what does the first constraint say? The green dot must be less than or equal to y1. So the green dot must be to the left of this guy here, right? And the second constraint here says that this green dot here must be to the right of this minus yi, right? And likewise for these two. Okay, so when we do the minimization slowly, okay, we are reducing y1 and y2 separately. So as we are changing y1, at some point, this bar here, lower limit, will hit this green dot, right? And we cannot lower y1 any further because it will violate this constraint. Agreed? And here, as we minimize y2, lower y2 gradually, at some point, y2 will hit this green dot, right? And that's when x1 plus 4x2 minus 5 is equal to y2. Do you guys see this? Okay, so this is what happens. So these two become the active constraints. In our simple example, when x1 and x2 are fixed. Okay, but do you see what's happening to the y's now? Okay, but now x1 and x2 are also design variables. Okay, so if we change x1 and x2, these green points will also change. So maybe some other x1 and x2 will result in this and this being the values of 2x1 plus 3x2 minus 3 and x1 plus 4x2 minus 5. Maybe. Okay. So what happens when we change x1 and x2? We change the position of these green dots. And that allows further minimization of y1 and y2, which means more movement of y1, of these two vertical bars inwards, and simultaneously movement of these two vertical bars inwards until again they hit the limits. Okay. So this is what's happening when we simultaneously minimize x and y. You separately saw the roles of x and y. Okay, and so this is a way to accomplish L1 norm minimization. L infinite norm minimization. Okay, what's the difference between one norm and infinite norm? In the one norm, we have the summation of the absolute values, right? That defines the one norm. The infinite norm is the max of the absolute values, by definition. So if this is the ith element, oops, anyway, so this is the ith element, this should be summation j. It's a typo here, well, two typos. This is summation j. Okay, so this is the ith element. So what we are trying to do is maximize. So we have all the different absolute values. Each element of ax minus b, we have a different absolute value. What's the infinite norm of ax minus b? The maximum of those absolute values, right? So what we want to do is minimize with respect to x. This is the objective function. Maximum with respect to each of the rows or each of the elements of ax minus b separately. Take the maximum of those that we want to minimize. Okay? So this is the L infinite norm by definition. Just ignore this summation j here. Okay, so this is, we define y equals max I ax minus bi. Okay, now look at the difference here. In the L1 norm, we had y as a vector, one for each element of this ax minus b. Now we just have a single y because we want to maximize not the summation of the absolute values, but simply the maximum. Okay, and so this is what we want to minimize. Simply minimize y and subject to these constraints. Or since this is the max, y is the maximum of those absolute values, each of those rows of ax minus b, each of those elements of ax minus b must be less than or equal to y, and each of those elements of ax minus b, ith element, must also be greater than or equal to negative y, right? So, in short, ax minus b, the whole vector is less than or equal to y times one vector, and ax minus b is greater than or equal to negative y times a vector of all ones. And y must be obviously greater than or equal to 0. This is scalar 0. Okay? So this is L infinite norm maximization. And so we just have one bound. All the ax minus b i's remain within these bounds. Okay? And we'll try to minimize and we'll hit the maximum of those. Okay? Is this clear now? Okay, so this is how we accomplish L infinite norm minimization using linear programming. Dual of linear programming. So this is the primal, minimize C transpose X subject to these constraints. Ax greater than or equal to B and X is greater than or equal to 0. This is called the canonical form. You also have another formulation of LP which includes inequality constraints, not equality constraints, okay? But that's, it's there in my lecture notes. But anyway, so this is the canonical form. And so now let's create the Lagrangian. Lx lambda mu. So we have, note here, I usually use mu to denote equality constraints, correct? But here, mu corresponds to these inequality constraints. Okay, so mu is also like the lambda, the dual variables for inequality constraints. In other words, both lambda and mu must be greater than or equal to 0. Okay, and why do I have a negative here in the Lagrangian? Because we have a greater than or equal to here. So that's why I put a negative here to maintain lambda greater than or equal to 0. And similarly, I have a greater than or equal to here, x is greater than or equal to 0, so I put a negative sign here. So that mu is greater than or equal to 0 too. Now I bring all the terms containing x here. So this is all the terms containing x, and this is the term that doesn't contain x. This is the Lagrangian. What do we have to do? Theta d lambda mu equals infimum of the Lagrangian with respect to x. Correct? Okay. Now, what will this be? Which is equal to, now this lambda transpose b does not contain x. So we can take it outside the infimum. So lambda transpose b plus infimum of everything inside. Okay. This is a vector transpose times x. What will be the infimum? It can be negative infinity, right? If we select our x's in such a manner, okay, this might have some negative terms, and so we can select the corresponding xi to be anything greater than 0, and so, well, it's unrestricted here, right? This infimum is unrestricted. We don't care about x being greater than or equal to 0. So we can choose x any way we like, and so this is, the infimum has no bound, right? The infimum can be negative infinity, except in one case, when the quantity inside the parenthesis is 0. In that case, what happens? The infimum, this entire term vanishes, correct? So in other words, this is theta d lambda mu. Lambda transpose b when what's inside parenthesis, this column, this is a row vector, not a column vector. So this condition is satisfied. C transpose minus lambda transpose A equals mu transpose. When this condition is satisfied, okay, in which case this vanishes, the second term vanishes, and we are left with lambda transpose B. So theta d lambda mu equals simply lambda transpose B, and it's equal to negative infinity otherwise. Okay, now what should we do? We want to, remember, we do the minimization and then the maximization, correct? So we want to maximize with respect to the dual variables, lambda and mu. So now we want to maximize theta d lambda mu. Okay, so we want to formulate the dual problem. Okay, we want to maximize theta d lambda mu. That entails this possibility too, it being negative infinity, right? So we can safely discard this possibility. Since lambda and mu are variables, as long as we satisfy this condition of lambda and mu, then this will be what we want to maximize. Correct? Okay, so this is the primal problem. This is theta d of lambda mu. We want to maximize theta d lambda mu, so we drop this case where it's negative infinity. Just ignore it. It's not going to be, it's at our liberty to adjust lambda and mu any way we like to do the maximization. So why even consider this case? Okay, so we have this case. we have to consider only when C transpose lambda minus C transpose, minus lambda transpose A equals mu transpose. That both sides are row vectors. I'll take the transpose. So C minus A transpose lambda equals mu. Okay, now this is interesting because you get a direct relationship between lambda and mu. You can just eliminate mu, right? We can eliminate mu, but we must ensure that mu is positive, right? So C minus A transpose lambda must be positive, greater than or equal to 0. And with that constraint, we effectively don't need mu anymore. So this is theta d lambda mu, lambda transpose B, and mu must be greater than or equal to 0, which means that this must be C minus A transpose lambda must be greater than or equal to 0. Now we are in a position to write down the dual form of this LP. We want to maximize this. Maximize with respect to lambda, B transpose lambda. That's our objective function. And this is our constraint. Because, and then we have this. This takes care of the mu greater than or equal to 0 constraint. And so lambda must be greater than or equal to 0 too. So this is the dual formulation. This is the primal form of the linear programming. This is the dual form. Okay. Observe what happens. These bounds here in the constraint get transformed here. They get incorporated in the objective function. On the other hand, this C here, the coefficients of the objective function, move into the constraint. A becomes A transpose, and then greater than is replaced with a less than. And we have this. So this is the dual. This is the primal. We'll next see what the lambdas mean physically for the linear programming problem. Okay, we'll give it a very physical interpretation. Okay, strong duality holds. So before we, that's in the next slide. So now here, before we go into that, I can just tell you that for linear programming, strong duality will hold. Okay, which means that B transpose lambda star will be equal to C transpose X star. But if the primal is unbounded, so it accepts infinite as a solution, okay, then what happens to the dual? The dual becomes infeasible. It accepts no solution. On the other hand, if the primal is infeasible, this is infeasible. Okay, there's no way to satisfy all of these. Then the dual is unbounded. It accepts lambda equals infinity. Okay. Otherwise, if both are feasible, if one is feasible, then the other is feasible, and C transpose X star equals B transpose lambda star. And the proof of this is, I think I put them in the lecture notes, but it's optional. You don't have to read the proof. It will be good if you do. Now, let's interpret the dual, okay, for a linear programming. We want to minimize with respect to x1 and x2, 9x1 plus 8x2, subject to x1 plus x2 greater than or equal to 5, and 3x1 plus twice x2 equals greater than or equal to 10, and of course x1, x2 must be greater than or equal to 0. So this is our primal problem. We have, excluding this first quadrant constraint, we have two constraints. Okay. Now, I can form other constraints out of these two constraints. Okay, as long as I'm not multiplying these constraints with anything negative, if we multiply it with something negative, then the sign changes. So this greater than equality will become a less than equal. So, okay, for instance, I take 1 times the first constraint plus 1 times the second constraint. I get this constraint. 4x1 plus 3x2 is greater than equal to 15. Okay, in other words, 15 is a lower bound of 4x1 plus 3x2. Okay, I can multiply the first constraint with 2 and the second constraint with 1. And then I get this as another constraint. 5x1 plus 4x2 greater than equal to 20. So 20 is a lower bound of 5x1 plus 4x2. Likewise, 2 times each of these constraints added up gives you this. Okay, 8x1 plus 6x2 is lower bounded by 30. So 8x1 plus 6x2 will always be more than 30. Okay. And likewise, we get yet another constraint, and then we get a really large value here, 150, when we multiply both by 10. Okay. So there are various ways in which we can formulate new constraints. They will always be linearly dependent, of course, on these two constraints. So we can formulate all these new constraints any way we like. But what's the purpose of all these new constraints? Well, here's another example, 310. Okay, now, so I told you that 15 is a lower bound of 4x1 plus 3x2. Notice that x1 and x2 are always positive. And compare the objective function. It's 9x1 plus 8x2. And look at this constraint here, 4x1 plus 3x2. Okay, just look at the left-hand side here, 4x1 plus 3x2. And here we have 9x1 plus 8x2. Which of these two will necessarily be more? 4x1 plus 3x2 or 9x1 plus 8x2? Since x1 and x2 are positive, look at the coefficients. 9 is more than 4, 8 is more than 3, right? So this objective function is always greater than this 4x1 plus 3x2. Why? Because 9 is more than 4 and 8 is more than 3, correct? If this 15 is a lower bound of this, then it also is a lower bound of the objective function, right? So this is a pretty relaxed lower bound, 15. But now, the other constraint that I formulated out of these two is this. Okay, and so 20 is a more tighter lower bound of the objective. Because if you look at the coefficients, 9x1, here you have 5x1. So 9x1 will always be more, can never be less than 5x1, right? So likewise, 8x2 is greater than or equal to 4x2, right? So this here, 5x1 plus 4x2 is always less than or equal to the objective function. Therefore, 20 is also a lower bound of the objective function. This is tighter than the 15, right? We don't need this anymore if we know that it's the objective function must always be more than 20. We're trying to minimize the objective function, right? So why do we need 15? We have, with this knowledge, we are better off, right? Okay, we know that when we minimize, we can never go below 20. But this constraint here establishes 30 as another lower bound. And this is tighter, right? And 35 is another lower bound. So we're now getting progressively tighter and tighter. This is very close, actually. 9x1 plus 8x2, and this is 9x1 plus 7x2. Correct? Okay. So now we have all these. We have progressively tighter and tighter lower bounds of the objective function. Okay, maybe we'll get something close to 35, 36, 37, 38, 38.5, 40, something like that. Okay. When we do the minimization, because this is very close to the objective function. Is this a lower bound, 150? No, because compare 9x1 with 40x1 here. This is actually more, right? And 8x2 here with 30x2. So this actually is more than the objective function. So who cares if something more than the objective function has a lower bound of 150, right? It doesn't mean that 150 is a lower bound. The same applies to 310. So 310 is not a lower bound. Why is that? One of the coefficients here, if it exceeds one of the coefficients here, the corresponding coefficient here in the objective, then we discard that, right? Okay, so we gain some knowledge about what the minimum of the objective function will be. We know that it will be a little above 35. Okay. Now let's try to generalize this. Instead of just arbitrarily trying to construct progressively larger lower bounds of the objective, what we shall do is, let's pick weights lambda 1 and lambda 2, greater than or equal to 0. Let me break the surprise. They are the duals. You'll see. Okay. So lambda 1 and lambda 2 are two weights that we will apply to this and this constraint. Okay, and they must be greater than or equal to 0, right? We cannot multiply one of them with a negative, because then this greater than or equal to would become a less than or equal to. Okay, so this is the general form of any additional constraint that we have. Okay, now what happens? I take the coefficients, so the terms containing x1 here, and these are the terms containing x2, and greater than or equal to this. This is what I have. When I simplify this, this is the constraint. This side is lambda 1 times 5 plus lambda 2 times 10. Okay, are you guys with me? So this 5 lambda 1 plus 10 lambda 2 is a lower bound of the objective function when? If this coefficient here of x1 is less than or equal to the coefficient, this 9 here in the objective function. And this coefficient here of x2, lambda 1 plus twice lambda 2, must be less than or equal to 8. Correct? So this is one constraint, this here. Okay, and so comparing these, we must have this constraint, and similarly, we get the other constraint from this and this. Okay, so this is a lower bound, and we want to push the lower bound upwards, correct? So we want to maximize this 5 lambda 1 plus 10 lambda 2. Okay, but provided these constraints are satisfied. So this is our primal. This is the lower bound of the objective function. Lambda 1 and lambda 2 must be greater than 0. And these are the constraints on lambda 1 and lambda 2. What is the maximum lower bound? We have to maximize this. Lambda 1 plus 10 lambda 2. So the new LP problem we get is this. Maximize this subject to these constraints. And of course, lambda 1, lambda 2 greater than equal to 0. Okay. So this is the dual. Any questions?
This example and this lower bound concept can also be visualized through graphical method, isn't it?
Oh, yes, of course. You can take the derivatives. Here, the derivatives will give you constants.
Yes.
Exactly, and you can do it at home. This is the primal. This is the dual. Questions? Okay, with this we end today's lecture, unless you have any other questions. Anywhere, if you have any other questions. Okay, so we end today's lecture then. We won't